So we've looked at our combustion theory and laid out that equation and talked about the air-fuel ratios and how we can calculate that air-fuel ratio. And I've said all the way through that this is ideal. This is the theory of what's going on, but we don't often get the theory happening the way we want to all the time, and we end up with some bad emissions. So where do they come from? That's what we're going to take a look at now. So let's go back to that generic equation, that generic combustion equation, where I put the question marks back in here. So this could be any fuel molecule. And again, almost all our fuels are made up of carbon, hydrogen, and oxygen, some combination of those. And maybe no oxygen, maybe some oxygen if it's an oxygenated fuel. And then we combine that with oxygen, and the nitrogen from the air, we kept saying it's just kind of passing through. So when we take the oxygen in, we naturally get some nitrogen with it, a lot of nitrogen actually. And so it hopefully goes out, and that oxygen gets broken up into carbon dioxide and water. So let's take a picture of how this has actually happened. So think about this. This fuel molecule, it gets broken down. So when we have heat, and again, we have a lot of heat that's going on here when we ignite this thing. So there's the heat is part of that reaction that's converting this. The heat breaks up that fuel molecule. So now for a split second, if you will, I've got these bunch of carbon atoms kind of floating around over here, and I've got hydrogen atoms as well. They've gotten broken up, so there's hydrogens, and they're floating around a lot of different places, and more carbons and more hydrogens. So that fuel molecule has been broken up. Now, hopefully, in this process, I've had, when in that combustion chamber, I've had this air mixed up in there with it as well. So hopefully, in with all those things, I've got some oxygen molecules. There are some oxygen atoms now, and the heat has broken them up as well. So I've got these oxygens floating around in there. And ideally, what I want to happen is every one of these carbons in that reaction is going to grab a hold of two of those oxygens that are floating around, grab a hold of them, combine with them, take them out the other side of the engine. So we could kind of maybe go with a bad high school dance analogy or something like this, and people coupling up or whatever, but however you want to think about it. But that one carbon, it's going to grab two of those oxygens, and it's going out as CO2 going out of the engine. So that oxygen, the hydrogens, they're running around looking for partners as well. And so hopefully we get two of those hydrogens that are going to find an oxygen. They're going to get together and combine, and that's going to make my water molecule. So there's my two hydrogens going with that oxygen. They're coming out as water, so they get together, and hey, there we go. We're happy and going on. But then we've got this carbon over here somewhere, and there's not enough oxygens over here. I didn't get good mixing for some reason. And when that carbon got broken off, he's looking around for somebody. Well, the only thing he sees is one oxygen. So he combines with that one oxygen. Oh, what am I ending up with? So if he only has one oxygen, what I really want coming out of there is CO2. But what I might get is C with one oxygen, because it couldn't find another oxygen to combine with. What is CO? That's carbon monoxide. Oh, that's one of our bad gases that we get out of an engine that we really would like to get rid of, right? So that's what happens. So there's not enough oxygen there. The carbon couldn't find something to combine with, and that kind of doesn't work out very well. So maybe I've got this carbon over here. He grabbed two of those, and maybe there's something else to grab that oxygen. Well, there's a carbon sitting right in the middle here, and that carbon, he couldn't find anybody to combine with. And so that carbon just goes out all by himself. So, so there's a carbon. Oh, what do we call carbon? If carbon just comes out, that's that black soot that we see coming out of. That's particulate matter. So this is what we call soot. All right, so that black coating on the inside of an exhaust pipe, or the black kind of a smoke that comes out of an exhaust sometimes when it's not running well, that could be just free carbon. So that's not good either. We don't want free carbon floating around. We really want that combined into carbon dioxide. So there we end up with carbon monoxide. What we may end up happening, and I could draw this out forever, but you may have some carbons, they can't find any oxygens, but there's some hydrogens kind of floating around there, so they kind of recombine with some of those hydrogens, and so we get a carbon hydrogen kind of a combination, and this, they could combine at different ratios and so forth, and so we have something, and it's almost like a fuel molecule that goes out, so kind of like unburnt fuel. These we call hydrocarbons. Hydrocarbons. So they're just carbons and hydrogens that kind of got back together, or maybe they didn't get broken up completely to begin with or whatever. So there it's like a different kind of a fuel molecule. And we often talk about unburnt fuel going out. Sometimes it is unburnt fuel, or sometimes it's kind of a recombination of some of those carbons and hydrogens, giving me these hydrocarbons that look like unburnt fuel. So there's a lot of those things that are going out of there. So that could be problems. Again, this is a problem if we don't have good oxygen mixing. We don't have oxygen molecules around everywhere. And that's one of the reasons why oxygenated fuels can sometimes help us out, because that carbon that was floating over here by itself, maybe because there was an oxygen in that fuel, it gives me a little extra oxygen over there near those carbons. So hopefully I don't get as much of this carbon monoxide and hydrocarbons and carbons, because I'm a little bit more oxygen there, so there's a little bit better chance of those carbons finding some oxygens to connect with to go out as carbon dioxide out of the exhaust. So that's part of what can happen there. So if we don't get complete combustion, so this is an incomplete combustion. When we have lower temperatures, it's not quite as hot, so we'll often see this. That's why a car will sometimes smoke a little bit when it starts up, or an engine will put out a little smoke when it starts, because it's not hot, the combustion temperatures are low, these carbons aren't finding everything that they need, and so we got some dirt, hydrocarbons, some soot and stuff coming out of the exhaust until the heat builds up. And so when we get the heat in there, this is going to start working better, because that heat's going to make those atoms go fly around more. They're going to be more active, so there's a better chance of them combining, the carbon and the hydrogens and the oxygens combining up in the way they should to go out of the outside of the engine. All right, so the heat coming up is going to help all this kind of stuff, but we left something out of this equation. We've kind of ignored something. We talked about the carbons and the hydrogen and oxygens over here that are all floating around. So, but we also have nitrogens in there, right? So we got nitrogens all in this mix as well. And if there's a lot of heat, they're going to get broken up. So that N2 is going to get broken up, and we're going to have free nitrogen atoms floating around. And now they're looking for somebody to mate up with, to be able to go out of the exhaust in the engine. So what do they find? So they look around and see what they can grab. So what do we grab? Oh, man. So maybe there's an oxygen over here or two with these nitrogens. And so one of those nitrogens might grab an oxygen. And so instead of going out as N2, it's going to be going out as NO. We call that nitric oxide. Not good, right? So, or it might be NO2, nitrogen dioxide, nitrous oxide. So it could be what we kind of categorize these as. We often say NOxes or NOx. So they could combine as nitrogen with one oxygen, nitrogen with two oxygens, nitrogen with maybe 3 or 4, whatever, but some nitrogen, combination of nitrogen with oxygen. NOxes, those are really bad gases. Oh, man, and so now we've got a trade-off in there. What's going on? So we want a lot of heat so that this reaction works good, and I don't get carbons, and I don't get carbon monoxide and these hydrocarbons and everything going out the exhaust. So I want the heat going up, but when the heat goes up, that breaks up these N2s, and they're going to grab some oxygens, and they're going out as NOxes, and it's like, that's not good either. So we got to clean this up. So again, there's going to be some trade-offs here, and we'll talk about that in just a minute. So what we'll look at next is, all right, we've got this mess. Ideally this is what should happen. In reality, this is what's kind of happening in there. So how do we improve that? How do we affect that? How do we clean it up so I don't have this stuff going out the exhaust of an engine?